So in this lecture, I will prove the closed graph theorem. So let me define the graph of a bounded linear operator. So we have x and y as before Banach spaces, and a map from x to y, which I'm assuming to be a bounded linear operator. So for that fixed map M, I will define the graph of M, which is the set of all points x, mx, in x times y, such that x belongs to x. So the set G is formed by all pairs x, mx, where x is a point of x. And this is, of course, a subset of x times y. And on that set, I will define a norm. So a norm of a point x, mx will be, by definition, the norm of x plus the norm of mx. So you see, on the one hand, it's clear that G is a linear space. I leave it to you to check that G is indeed linear. And I also leave it to you to check that if I define on G these, the norm, this quantity, I claim that this is a norm in G. And therefore, G, which is called the graph of M, with this norm becomes a normed linear space. So G is a normed linear space with this norm. So now that I defined the graph of the operator M, I will say that this operator M is a closed operator if the set G is closed. So you see, G is a subset of x times y, and well, if this subset is closed, I will say that M is a closed operator. So what does it mean that G is closed? Well, you take a sequence xn, m xn of points, so xn belongs to x. You take a sequence xn, m xn, which belongs to G. You assume that it converges with respect to this norm. So you assume that xn converge to x and that m xn converge to y. Well, if the graph G is closed, this implies, this requires that the point xy belongs to G, which means that y is equal to mx. So the condition for M to be closed is the following. Take any sequence xn which converge and such that m of xn also converge, then y is equal to mx. Okay? So what we are imposing when we are saying that M is closed is, I repeat, you take any sequence xn in x, assume that xn converge to some x, and that m of xn converge to some y, then y is equal to mx. So if this condition holds, then you say that M is a closed operator, and in fact, what you can see is that G, as a subset of x times y, it's a closed subset. So now, what I claim is that if M is a bounded operator, so remark, if M is bounded or continuous, then I claim M is closed. So let's prove that. Let's assume that M is bounded, and let's show that M is closed. So to prove that M is closed, we have to prove this property. So we fix a sequence xn in X, and we assume that xn converge to X, and mxn converge to Y. And we have to show that Y is equal to mx. But since M is bounded, we know that M is continuous. M is continuous means that if xn converge to X, then M of xn converge to M of X, because M is continuous. But now we have a sequence, mxn, which is converging at the same time to mx and to Y. So this implies that mx is equal to Y, and this is exactly what we wanted to conclude. So we just proved that if M is a bounded operator, then it's a closed operator. And actually, what the closed graph theorem states is that the converse is also correct. So if M is a closed operator, then it's a bounded operator. So this is what I'm stating next and proving. So before I state the theorem, let me make a remark. And the remark is as follows. Well, if M is a closed operator, then G, it's a complete linear space, which means that G is Banach. So let's prove that G is a Banach space if M is closed. So let's consider in G a Cauchy sequence. So let's assume that xn, M xn is Cauchy for the norm which I introduced, and let's prove that it converges. Well, since xn is Cauchy, so this pair xn, mxn, it's Cauchy, you see from the definition of the norm that xn is Cauchy. So this implies, by the definition of the norm, that xn is Cauchy. But X, it's a Banach space, so this implies that xn converge to some limit which I'm calling X. Now, let's look at the second coordinate. Well, the second coordinate, it's also Cauchy. So we also have that M of xn is Cauchy. Since Y, it's a Banach space, and this is a sequence in Y, well, this means that M xn converge. Let me represent by Y its limit. So now we deduce that xn converge, M xn converge. Since M is closed, this means that Y is equal to mx, and therefore what we proved is that xn is converging to X, and mxn is converging to mx. So this means that the pair xn, mxn, it's converging with respect to this norm to the pair x, mx, which shows that G is complete because we consider a Cauchy sequence, and we proved that this Cauchy sequence converge. So now we are ready to state the closed graph theorem. So this is the closed graph theorem, which says as follows. So you have M, a bounded linear operator from X to Y. Sorry, M, a linear operator, linear map from X to Y. X and Y are Banach spaces. And I'm assuming that M is closed. And what we will prove is that then M is bounded. So we have two Banach spaces, X and Y. We have a linear map, M from X to Y. we assume that this map is closed, and we will prove that it's bounded. And the proof is as follows. Well, consider the graph. Introduce G, the graph. Since M is closed, we have seen that G, it's a Banach space. So now let's define an operator A from G to X. So all points of the graph are pairs, X and X. And this map A from G to X sends this pair to X. So the pair X and X is sent to X by the map A. So now I claim that, well, A is linear. Well, that's clear from the definition, and I leave it to you to check that A is linear. Now I claim that A it's a bijection. And that also clear. Well, it's surjective, so it's onto. Fix any point in X. We want to find a point in G which is sent to this point X, but, well, the pair X and X is sent to X. So this map, it's onto. It's also one-to-one or injective. Assume that X1 it's equal, that A of X1 M X1 it's equal to A of X2 M X2. By definition of A, this means that X1 it's equal to X2. So X1 it's equal to X2. This implies that M of X1 it's equal to M of X2, and therefore that the pair X1 MX1 it's equal to X2 MX2, and this proves that A it's one-to-one. So A it's a bijection, a linear bijection. Now I claim that A it's bounded, and therefore we'll be able to use a previous theorem which tells us that if we have two Banach spaces, but in our case G it's a Banach space, and X it's a Banach space, X by assumption G because the operator it's closed. So the previous theorem tells us that if we have a linear bijection which is bounded, then the inverse of A it's also bounded. So let's prove that A it's bounded, but that's clear. If we take the norm of A, X, and X, well, by definition, A of X and X, it's X. So this is the norm of X. And of course, the norm of X, it's bounded by the norm of X plus the norm of MX. And this is exactly equal to the norm of the pair X and X. So this proves that the operator is bounded and that its norm it's less or equal than 1. So we proved that A it's a linear bijection which is bounded. So now we use a theorem from the previous lecture which tells us that since both spaces are Banach spaces, the inverse of A is bounded. But what is the inverse of A? Well, we can read it from here. So the inverse, it's a linear map from X to G, which sends X to the pair X and X. So this is the inverse map. And by the previous theorem, we know that this linear map, it's bounded. So we know that there exists a finite constant C0 such that a minus 1 of x, it's bounded by constant 0 times the norm of x. And this for all x in x. But what is a minus 1 of x? This is the pair x mx. So this is saying that the pair x mx, the norm of this pair, it's bounded by C0 times the norm of x. And by definition, it's written over there, the norm of this pair, it's x plus the norm of mx. So it follows from this inequality that mx So it follows from this inequality that mx, it's bounded by C0 minus 1 times the norm of x. And since this inequality holds for all points x in x, we have that m, it's bounded, and that the norm of m, it's bounded by C0 minus 1. So this proves that m, it's a bounded operator whose norm, it's bounded by C0 minus 1. And this is exactly what we wanted to prove. So I'll give you two applications of this theorem, which I wrote here to remind you. The first application is the following. So assume that you have now x, a linear space. And that on x, you have two norms, which are defined, norm 1 and norm 2. So these are two norms defined on x. So I'll say that these two norms are compatible I'll say that they are compatible if the following holds. Well, if xn converge to x in the norm 1, and the same sequence xn converge to y in the norm 2, so assume that you have a sequence of points xn in x, and this sequence has the following property: with respect to the norm 1, xn converge to x, and with respect to the norm 2, xn converge to y. I will say that they are compatible if for all x, y, and sequence xn, this implies that y is equal to x. So this is the definition of two compatible norms. And what I claim, so the corollary, say the first consequence of the closed graph theorem is the following. Well, assume that, so that you have x, a linear space, that you have in x two norms, 1 and 2. So I will assume that x with the norm 1, it's a Banach space. X with the norm 2, it's a Banach space. So x endowed with the norm 1, it's a Banach space. And x endowed with the norm 2, it's a Banach space. I will assume also that norm 1 and 2 are compatible. So that this property holds. And what I claim is that under these three conditions, so that the norms are compatible, that x with norm 1 is a Banach space, x with norm 2 is a Banach space, then I claim that the norm 1 and 2 are equivalent. So 1 and 2 are equivalent. We have already seen that, so let me just remind that two norms are called equivalent if there exist finite constants and strictly positive C1 and C2, such that C1 x, the one norm of x, it's bounded by the two norm of x which is bounded by C2, the one norm of X, and this for all X in X. So recall, two norms are said to be equivalent if there exists a strictly positive constant C1 and a finite constant C2, such that for any X, C1 times the one norm of X, it's less or equal than the norm of the two norm of X, which is less or equal than C2 times the one norm of X. And this result says that if you have two norms which are compatible, and observe that in these two norms I don't make any assumption on their relations, but if two norms are compatible, and if they make the space X Banach spaces, so both make X Banach spaces, then actually they are equivalent. So there exists these constants C1 and C2 with this property. So I'll prove now this theorem. So I'm proving the following corollary. X, it's a linear space. We have two norms defined on X. These two norms I assume to be compatible, and X with the one norm and X with two norms are Banach spaces. Then I'm claiming that the one and the two norms are equivalent. So let's prove that. So the proof is based on the closed graph theorem. So I'll define a map A from X with the one norm to X endowed with a two norm. And this is just the identity. A is just the identity map. So A sends X to X. And what I claim is that A, it's a closed operator. Okay, it's clear that A, it's a linear operator. So let us show that it's closed. To prove that it's closed, we take a sequence xn such that xn it's converging to x, and axn it's converging to y. And we have to prove that ax it's equal to y. So we know that xn is converging to x. This means that xn is converging to x in the one norm. Now, axn converging to y, we are in the second space, and in the second space we are working with the two norm. And A is the identity, so axn is actually equal to xn. And what this second statement is saying is that xn is converging to y with respect to the two norm. So this sequence xn, it's converging to x in the one norm, and it's converging to y in the two norm. Since these two norms are compatible, it follows from these two properties that x is equal to y. But since x is equal to y it's ax, because since x is equal to y, A it's the identity, so ax it's x, but x it's y, so ax it's equal to y, and this is exactly what we wanted to prove. So let me repeat. We know that xn is converging to x in the one norm. On the other hand, axn is converging to y in the two norm, but a of xn, it's xn. So the sequence xn is converging to x in the one norm, and it's converging to y in the two norm. From that, since the two norms are compatible, we know that x is equal to y. So x is equal to y because the two norms are compatible. On the other hand, A it's the identity, so x it's equal to A of x. And from this identity, we conclude that A of x it's equal to y, and this is exactly what we wanted to prove. So this shows that A is a closed operator. Now, the closed graph theorem tells us that A it's bounded. A it's bounded because both spaces are Banach spaces by assumptions. So A, it's a bounded operator, and therefore there exists a constant C1, finite, such that the norm of AX, and here the norm of AX, we are talking about the second space, so this is the 2 norm, it's bounded by C1 times the norm of X, but the norm of X is the 1 norm. And AX, A, it's the identity, so this is actually equal to the 2 norm of X. So we proved that the 2 norm of X, it's bounded by C1, the 1 norm of X, for all X in X. So this gives us one inequality, and the other one, it's obtained by replacing 1 by 2 and 2 by 1. So you get the symmetric inequality, and that completes the proof of the theorem, right? So here is one inequality. So now if you replace 1 by 2, what you get is the 1 norm of X. It's bounded by the 2 norm of X. And with that, you have the 2 inequalities which we claimed, or which shows that actually these 2 norms are equivalent. So in the second application, I consider a space X, which is a Banach space. And I'm assuming that X can be written as the direct sum of 2 subspaces, AB. So I'm assuming that AB are closed subspaces of X. And saying that X, it's a direct sum of A and B, means that if you take any point X in X, you can write it X as a sum of an element of A plus an element of B. And that this decomposition is unique. So if X, it's equal to A1 plus B1 and also A2 plus B2, where A1 and A2 belong to A, B1 and B2 belong to B, then A1 is equal to A2, and B1 is equal to B2. So here I'm assuming that X can be decomposed as a direct sum of 2 closed subspaces of X, and by saying that X is a direct sum means that any element of X can be written as the sum of 1 element in A, 1 element in B, and that this decomposition is unique. Now, by assuming that, I will define an operator P, A, which X sends X to A, and you take an element X, it has a unique decomposition as A plus B, and I will send this X to A. Of course, P of A, it's linear. Again, I leave it to you to check that P of A is linear. And what I claim is that if you take an element A of A, then PA of A, it's equal to A. So that on A, PA is the identity, and this is clear because you can always write A as A plus 0. So A, it's an element of A, 0, it's an element of B. This decomposition is unique, and so this linear map sends this element A to A. So this is exactly what I claimed. So PA acts as the identity on A, and PA projects the set B to 0, because again, if you take an element B of B, you can always write it as 0 plus B. This decomposition is unique by assumption, and therefore, by definition of the map, you send B to 0. So PAB is equal to 0 for all elements B in B. So PA, it's sending, acting as the identity on the set A, and PA, it's projecting any element of B to 0. In particular, you have that PA square, it's equal to PA, right? Because, well, when you apply PA once, you get an element of A, and therefore, if you apply it a second time, since it's working as the identity over A, it's equal to PA, right? So the fact that PA, it's acting as the identity on A, you can get that PA square. So here means that you're composing PA with PA, but since PA acts as the identity on A, the second time you apply it, it's just the identity. So you get that PA composed with PA is equal to PA. And also, if you first take any element of X, as you apply PB, you get an element of B. Then when you apply PA to an element of B, you get 0. So this is 0. I will say that an operator M such that M squared is equal to M to be a projection. So definition, so let me write it here. An operator, a linear operator from X to Y to X, is a projection if M squared is equal to M. And here we just proved that PA and PB are projections, and moreover, PA PB is equal to 0, and PB, of course, if you apply first A and then B, this is also equal to 0. So for the moment, I just introduced two projections, PA and PB. We showed that they are linear, and they are projections, and they have these properties. And this is all based on the fact that I am assuming that I have a Banach spaces, which can be written as the direct sum of two closed linear subspaces of X. So what I claim, and this is my second application of the closed graph theorem, is that PA, it's bounded. So remember, X, it's a Banach space, and X can be written as the direct sum of A plus B, where A and B are closed linear subspaces of X. And this means that any element X can be written as a sum of one element of A, one element of B, and that this sum is unique, that these elements A and B are unique, that the composition is unique. And then we defined a projection, PA, which goes from X to A, and which sends X to the element A, which appears in its decomposition. Since A is closed and X is Banach, it's clear that A is a Banach space, so A is complete. Now, to prove that PA is bounded, we will use the closed graph theorem. The closed graph theorem tells us that in order to prove that this linear operator is bounded, and this is a linear operator between two Banach spaces, the only thing I need to show is that the graph of P, so GA, which is the graph of PA, it's closed. And what does it mean that, to prove that GA has a closed graph. We take a sequence xn in X, and we assume that xn converge to X, and that PA of xn converge to some A. And we have to show that PX, PAX, it's equal to A. And to prove that the graph GA is closed, we have to show that for any sequence xn in X, which converge to some X, and such that PA of xn converge to some set point which I'm representing by A, then PA of X is equal to A. So let's prove that. Well, xn belongs to X, so it can be decomposed in a unique way as an element of A and an element of B. So we know that xn can be written as an plus bn, where an belongs to A and bn belongs to B. Now, PA of xn, by definition, it's equal to an. So we know that xn is converging to X, and PA xn is converging to A. So PA xn is converging to A. So this means that an is converging to A. X, so let me write here, X can also be decomposed. So X can be written as A prime plus B prime, where A prime belongs to A and B prime belongs to B. Now let's look at this decomposition. Xn, it's an plus bn. Xn is converging to X by assumption. PAxn is converging to A, but PAxn is an. So an is converging to A. And since xn is converging to X and an is converging to A, bn converges. So let me represent by B the limit of bn. I know it exists because I know that xn converge and an converge. Therefore, xn minus an, which is bn, converge. So let me represent by B its limit. Since A and B are closed, and an belongs to A and bn belongs to B, A belongs to A, and B belongs to B. And also, since an is converging to A, bn is converging to B, an plus bn is converging to A plus B, but an plus bn is xn, which is converging to X, so X is equal to A plus B. Now, A belongs to A, B belongs to B, so this is the decomposition of X. We proved that this limit is equal to A plus B, and this is the unique decomposition of X because, by assumption, these decompositions are unique. Since this decomposition is unique, this means that the PA of X, which sends X to the point in A which appears in its decomposition, this means that PA of X is equal to A. And this is exactly what we wanted to prove. Right? So we proved that PA of X is equal to A. This shows, therefore, that the graph GA is closed. And if the graph is closed, this means that A or PA is a bounded operator. And this is exactly what we wanted to prove. Recall that here we are using the closed graph theorem, which tells you that if the spaces are Banach spaces, and we have an operator which is closed, then it's bounded. And so this proves the corollary, and with that, we conclude this lecture.